Hello, everyone. Welcome to this very nice video where we're going to link ideas from business and ideas from calculus. In particular, we're going to look into the relationship between the demand curve and the slope of the tangent lines. And also, we're going to look into the notion of elasticity of the demand, which is something that we can compute using also differentiation. So first up is the relationship between the demand curve and the slope of the tangent lines on that curve. So the demand curve is essentially, mathematically speaking, an equation that links two quantities. The first one, the price of your product that you're trying to sell, typically we'll be using P for price, and the quantity demanded or the quantity sold to the public, typically we'll be using Q. And here there's a very nice relationship for that links together the quantity and the price. And that relationship is summarized in business as the law of demand. And the statement goes as follows: as the price of a good increase, so if you increase the price of your product, the demand or the quantity demanded decreases. So you're going to be typically selling less. And vice versa, in the sense that if you do decrease your price of your product, you're expecting to sell more. So I have this nice little cloud here. Yeah, boom. Okay, so in other words, if the product is cheaper, you sell more. Okay, so that should be very, very intuitive. This works in general. There are special cases, of course, but this is typically what's going on. So when you illustrate the relationship between those two quantities with a graph, typically you get the following curve. So if we use P as the independent variable and Q as the dependent variable, so on the X and Y axis respectively, the graph that links those two quantities will typically look like a decreasing function that I have in blue here. And if you pick any point on that graph and you compute the slope of the tangent, and of course, remember, that's really crucial. You're a master of calculus also, so might as well use this, that when you're computing the slope of the tangent, that's the same thing as computing the derivative of that function at that point. So remember, the derivative is, in this case, q prime or dq over dp. As you can see, when you look at this red line, the tangent line at that red dot, that point, this works for any point on that graph, but in particular for that point, you can see that this line has a negative slope because it's going down with the graph, of course. So the slope here is always going to be negative. So dq over dp is always going to be negative. And I have this summarize here: dq dp is strictly less than 0. So again, here we're just making this move from the definition in business, law of demand, and we're making it into a equation using calculus. So saying that as the price of a good increase, the quantity of the demand decreases. That's the same thing as saying the derivative is negative or dq dp is negative if you are using a function where the independent variable is price and the dependent variable is quantity. But sometimes, in some contexts, it's easier to go the other way around. Sometimes you will have the price as a function of quantity. So if you want to sell a specific amount, you want that price, the right price for it. But even if you change the x and the y axis, you're still going to get this graph. And I just replotted that graph for you. So boom, okay, you're still going to get that price, so that graph, sorry, for price that will be decreasing. If you pick any point, you're going to get something negative. But now price is the function as a function of quantity. So you will get that dp dq is also negative. So it does not really matter if you are using x, you're using p on the x-axis and q on the y-axis or vice versa. That derivative, these curves will always be decreasing. Those derivatives are always going to be negative. For the second concept, before introducing it, I want to end up this previous section with a nice remark. Sadly, this remark is missing from our notes because I'm the worst teacher ever. Okay, so the remark goes as follows. Of course, if the price goes up, the quantity you're going to sell are going to go down. But this means that you're making more cash per sale. So if you are selling one item at a higher price, you're making more cash on that sell. So that's very, very important. So maybe this is a good strategy to make more cash. But remember, as the price goes down, then you're selling more of them. So you might not be making as much money per sale, but you're making more sales. You're selling a lot more of them. So potentially by selling a lot more of them, you might be making more money. So what should we do? Should we increase the price at the price of selling less, but we're making more cash per sales? Or should we decrease the price and we're selling more? And even if we're making a little bit less money on each sell, overall, as you compute the total revenue, you're going to be making more cash. And the thing that answers this question for us is the notion of the elasticity of the demand. And that's our next section. Let's compute the demand elasticity. Our first definition for the elasticity of demand will be the standard definition that you see in a business or in an economics class. So the elasticity of demand is a formula, and that formula, the notation for elasticity is going to be small e in my notes. Sometimes we use also big E or epsilon. So the formula is the ratio of the percentage of change in quantity demanded over the percentage of change in prices. And here, the standard way to write that equation, so when you look at changes or variation in a business class, the typical notation is going to be delta. So if you're looking at the change of quantity, that's going to be delta Q. And because we're working in percentage, we just need to divide by Q. And for the denominator, if you're looking at the change in price, that is typically written as delta P. And because we're working in percentage, we divide by P. So another way to write that formula is the following. So delta Q over Q divided by delta P over P. And the absolute value is there because when we are referring to elasticity, we're typically talking about it as a positive quantity. But remember, the relationship between quantity and price is that as the price goes up, the quantity goes down. So typically this equation is going to be a negative value. So we put the absolute value in the definition. Sometimes in some books, they keep the negative value as part of the definition. Again, just get informed properly. So now, of course, let's go. And now let's look at the calculus version of the elasticity of demand. So the only difference between your standard classic equation from a business class versus the equation that you would see in calculus is that when we're talking about variation, instead of using delta, we're going to use differential term. So that delta Q here will be replaced by dQ, and the delta P is going to be replaced by dP. And now you have those two fractions that you can rearrange. So when you divide by two fractions, you can multiply by the flip of that fraction, and you can rearrange this elasticity equation as price over quantity. These values are, of course, positive, times dQ dP. What a coincidence. That dQ dP, we just talked about it, and we know that this quantity is always, always negative. And that's why we also put an absolute value here in order to make this quantity, this elasticity, when we're talking about it, positive. But this computation, if you just did P over Q times its derivative of dQ over dP, you would be expecting a negative value. And again, in some calculus books, when you are computing elasticity, they keep the negative sign with the definition. Again, just make sure you read this correctly. And actually, me personally, I don't really like this definition because it just looks like a nice formula that is kind of tweaked from the business formula, but there's a very nice origin for that equation using the revenue function and using maximization ideas that we saw in the first section of this chapter. I'm not going to cover the origin story in this video. So everything that is highlighted here in orange, I'm going to skip because I'm going to, in a different video, spend some time just explaining the true origin story of that definition. And to me, this is like super marvelous. But practically speaking, once you have the formula, you can start computing things. So if your goal is just to compute, and use some of those answers to make some conclusion, you don't really need, the origin story from that formula. So in this video, I'm skipping where this formula is coming from. I'm skipping the origin story, okay, for that definition. But if you're interested, in my next video, I'll be talking about this formula again and just giving you a nicer way to truly get this equation from scratch. Anyways, now let's see how we can use this elasticity in practice. So here we go. So the next definition is, what are the possible values for the elasticity for epsilon? Well, there's actually three scenarios. Typically, two of them are interesting and the third one not really, but there's practically three scenarios. Because of the absolute value, everything is positive. But the key number, the threshold that makes a huge difference, is actually the number 1. So the first scenario is that if the elasticity is greater than 1, then we say that the demand is elastic. Meanwhile, if the elasticity is less than 1, we say that the demand is inelastic. And if the epsilon, the elasticity, is exactly equal to 1, which will rarely happen, then we say that the demand is unit elastic. All right, that's a bunch of terminology. What does that mean? Okay, so the next remarks are absolutely essential to really understand how you can use this number to make some important decisions. So I'm going to start with the second remark. So the difference between elastic and inelastic. So when the demand is elastic, the business should consider decreasing the price to increase the revenue. Of course, remember the goal is to make some cash. You want to increase the revenue. What should you do? Should you decrease the price and sell more? Or should you increase the price, sell less, but making more money per sell? So if the demand is elastic, so if you compute epsilon and you get something that is strictly bigger than 1, then what you should do, you should be decreasing the price in order to make more cash. So here, in other words, by reducing the price, you will increase the number of sales, and this will generate more revenue to compensate the fact that you're losing some money per sale. So you will make more money if you decrease the price, or if when E is greater than 1. And then if the demand is inelastic, then the business should consider increasing the price to increase revenue. So here in both remarks, we want to make more cash. And we have two options. Should we increase or decrease the price? So if you are increasing the price in that second scenario, you're going to be increasing the revenue. So even if you're selling less item, the amount of cash that you're making more per sale will generate more revenue. Even if you're selling less, you're making more cash. So that's the big difference. So for elastic, decrease the price to make more cash. For inelastic, increase the price to make more cash. Okay, so absolutely crucial. And actually, you can also use this mathematically, this number, to make some calls. So if you have that elasticity number, okay, so suppose you compute your elasticity and you have that number, you can use that number to predict or to compute what will happen to your demand or the quantity that you're going to sell. So if you multiply elasticity with the percentage and change of price, so suppose you're thinking about increasing the price by $2. If you multiply that increase, that 2 by the elasticity, you're going to be computing the percentage of change in the quantity demanded. So when you go E times the change of price, you're going to get the change in demand. And the best way to assimilate this formula for elasticity and also to assimilate how you can use that number and also to assimilate what you should do as a business should you increase or decrease the price. Let's do some examples. All right, our first example, suppose the equation of demand is given by Q equal to 45 minus P squared over 5. And suppose this equation is defined for P between 0 and 15. Here, the interval is given just to make sure that the quantity of this equation is always positive. So our model needs to work for positive quantities. So again, as usual, Q is quantity. Read these questions correctly because sometimes there's units involved. So here in that equation, we're going to assume that quantity is going to be given by units of hundreds. And then P is just the price in dollars, so regular dollar. So the first question is, let's compute the elasticity of the demand when P is equal to $10. And then, of course, as soon as you have that elasticity number, you're going to answer if the demand is elastic or inelastic. So here we go. So for part A, so here, because my solutions were so nice, I'm just going to highlight what's going on. So for part A, so the first thing in these questions, price needs to be specified. So the P value, so label your P correctly. So P is 10. Okay, so here $10. And then the first thing you always do is you compute the corresponding quantity. So we have the formula for quantity. So you just compute the output of quantity given, that's your demand curve, given in the formula. So you're just replacing P by 10 in the formula. So 45 minus P squared, so 10 squared divided by 5. You can verify that this gives you a nice clean 25. So at $10, you're going to be selling 2,500 units. Okay, so but here you keep the numbers as they are. So here 25 is you don't have to worry about, it's just if you have to talk about it, then you talk about it. So next up is to use the elasticity demand, and in that formula we have that derivative dq over dp. So the third point is always, let's compute the derivative of dq dp. So 45 goes to 0. The derivative of p squared is 2p. So you get minus 2p over 5. That's my derivative of my quantity equation. And then as soon as you have the derivative, you want to compute some numbers. So you just compute the output of that derivative. So here I'm using dq over dp slash p10, which means you're computing q prime at 10. So sometimes that notation might be easier to follow. So computing q prime at 10, that's the same thing, just different notation. So you're just replacing in your formula, you're replacing the p by 10. So minus 2 times 10 over 5, you will get minus 4. Again, this is completely natural, and it's actually essential when you're doing these computation, when you're computing the derivative and you're replacing your p by your price, you will always get something negative. Okay, so because of the law of the demand, that derivative needs to produce negative quantity. So this means that epsilon, so the elasticity is going to be given by the formula. So it's the absolute value of P, so 10 over Q25 times the derivative of Q at 10, which is freshly computed to be minus 4. And if you do this computation in absolute value, you will get 8 over 5, also known as 1.6. So since the elasticity is bigger than 1, the demand is elastic. And again, what does it mean when the demand is elastic? It means that you should be decreasing the price in order to make more cash. Okay, so that's actually the answer for the C part. But anyway, so let's answer now the B part. So what is the percentage change in demand if the price is going to be increased to $11? Okay, so you want to increase the price to $11. What will happen to your demand? Like, what will happen to your sales? Again, I love this B part because it's a nice way to understand how you can use that number in an actual business context. So if the price is going to increase to 11, the first thing that you have to compute is that delta P, that percentage in change in price. So the percentage change in price, well, it's the new price minus the old price. And because you want a percentage, you're just dividing by 10. So increasing to 11 means you're increasing by $1, and $1 is 10% of the original price. Okay, so your variation. So when you say, hey, I'm increasing my price to $11, that's the same thing as I'm increasing it by 10%. Okay, so that's the only thing that we're doing here. Now, if you want to predict the percentage change in quantity demanded, well, take your elasticity number, which is 8/5 times 10%, and you're going to get another percentage. So here, 16%. So what is that 16? What does that 16% represent? So we expect the demand to decrease by 16%. Remember, when you're increasing the price, you're always going to be decreasing the demand. So that's always the answer here. You get a percentage that is a percentage of decrease if you're talking about an increase in price. And typically in our class, I will not, spin that question too much. I will always say, hey, I want to increase my price. What happens to the demand? So again, here, I've already mentioned this, but because the demand is elastic, increasing the price will decrease the revenue. And be careful, like there's two decrease here. You're always going to be getting a decrease in demand, but in this case, you also get a decrease in revenue. So because demand is elastic, to increase revenue, you should be considering decreasing the price of your product to make more cash. Next example. So we have the demand curve. Q is equal to 1000 e to the minus 0.02 p, where p is positive. This will make sure that Q is also positive because the exponential function only spits out positive quantity. So the units for Q here, we are in hundreds of units, and P is simply in dollars. So first question, when the price is 40, let's compute elasticity, and then let's decide if this demand is elastic or inelastic. So part A, so what you have to do is find P, find Q, compute T derivative of Q with respect to P, and then find its value for P equal 40. So in this question, so the P is always given, so we are at $40 right now. The quantity that you're going to sell at $40 is given by the demand curve. You simply have to replace P by 40, and you can double check that this will give you 1000 e to the power of minus 0.8. My advice is to keep this number pure because you're going to be using it in the formula for elasticity. So the real issue now, or the real computation, is to compute the derivative of Q with respect to P. This is a mini chain rule. We have e to the power of some stuff, so you get e to the power of that stuff again, times the inner derivative, which is minus 0.02. You keep the 1000 up front, and now you have your derivative. Now, if you evaluate your derivative at 40, so simply replacing P by 40 in that freshly baked derivative, you can verify that this will give you minus 20 times e to the minus 0.8. And of course, here a very nice remark, this quantity will always be negative. Remember, The derivative of a demand is always negative. So this is a good way to catch any mistakes if you don't get a negative value here. And now for the elasticity, the only thing you have to do is plug all the right numbers in the right spot. So it's P, so 40 over Q, which is 1,000 e to the minus 0.8, times the derivative of Q at 40, which we freshly computed to be minus 20 times e to the minus 0.8. You can see here, because we did not simplify, these e's will cancel perfectly. And after you multiply 40 with minus 20, you're going to get minus 800 over 1,000, which is in absolute value 0.8. Oh yes, now we have our elasticity. So we want to check if it's bigger or smaller than 1. Now my elasticity is 0.8, and that quantity is smaller than 1, which means that the demand is inelastic. And typically, I like to comment on what it means right away. So here, if we do part C first, so based on this number, based on the elasticity number, so let's predict what we should do with the revenue if we increase, should we increase or decrease the price to make more cash? And here, because the demand is inelastic, increasing the price will increase the revenue. So even if the quantity will go down, you're going to make so much more cash per sale that this is the right strategy. So because the demand is inelastic, to increase revenue, which is always the goal, you should consider increasing the price. Okay, so, and then we have an example of the effect of this inelasticity with part B. So what is the percentage change in demand if the price increases to $42? So right now it's at 40 and we're increasing to 42. So we're increasing the price by $2. We want to know what will be the effect on the quantity. So of course it's going down, but we want to know by how much. So if the price is increasing to 42, the percentage, remember it's always in percentage here, of the price increase. So it's the new price minus the old price. So 42 minus 40 over the old price. So it's an extra $2 on a $40 item. So this is 1 over 20 or 5%. So $2 increase is a 5% increase. So now if you want to compute the percentage change in quantity, it's the elasticity demand number that we just freshly computed to be 0.8, and we multiply this by 5%, and you're going to get 4%. So what is this 4%? What does that 4% means? Is that we expect the demand to go down. It always goes down. If you increase the price, it goes down. So it will go down by 4%. So you can see here in the inelastic cases that that percentage is always lower, because if the elasticity number is less than 1, then when you're multiplying it by the percentage change of price, you're going to get a new percentage that will always be smaller. Anyway, so that's it for those two examples. And that's it for that section. Again, if you are interested in the origin story of the elasticity demand, I will create another video. But for now, that's it. That's all. Bye bye, lo.